Hi everyone. I am Srishti, and today I'll be presenting the Kaggle competition Hotel ID to Combat Human Trafficking 2021. This was part of fine-grained visual categorization workshop at CVPR 2021, about which I'll be talking a little bit later. So this, as I said, this was from CVPR 2021 FGCV competition. If you're interested in listening to the competition discussion live or ask questions to authors themselves, it is tomorrow, that is June 25, 12:30 p.m. PDT or 2:30 p.m. Between 12:30 to 2:30. And they also have a Slack channel, so you can ask questions on Slack if you want to ask them. A little about me. I'm a graduate from SFU. I did my master's and I specialized in computer vision. Fun fact, tomorrow's my convocation, same time. So I'll be graduating soon. I'm currently at Mila. It's a research institute in Quebec, and I'm wrapping up my work this month. I've experienced mainly low short learning and class imbalance problems, which was also part of my thesis and also part of the internships I did. This leads me to my internship. I interned at EarthCast last year, where I worked on machine learning problems on satellite imagery, and I'm currently in the job market for ML and data science roles. I also have a website where I have put literally everything about professional. So yeah, you can put most update details there. Coming to the competition, a little bit of background on the competition. So the motivation for this competition was to combat human trafficking. The victims of human trafficking are often photographed, and investigations become difficult because different photographs have different qualities and different angles. So the initiative came out of Traffic Cam, which allows travelers to submit photographs of the hotel rooms. It is not exactly rural. So it does not mean a person is necessarily there in the photographs of the room. It can be just the plain photographs of the hotel rooms. And then we use, they use these images to identify where a person was possibly kept hostage when they were being trafficked. And these are the images which we'll be using as part of this competition. The organizers, I already mentioned, FGVC version 8 workshop at CVPR. Prizes, there were no prizes. It was a research competition, but the winners, the top 3, were given the opportunity to present their work in the workshop. It will be a good thing to point out that since it was optional, so tomorrow if you do attend, it is not necessarily that you will meet all the winners there. For example, some people have signed up and some have not signed up. I attended one of the post sessions today, and coincidentally, this workshop organizers were there, and they told that, okay, we have few people signed up, but not everybody has signed up. Dataset is Traffic Cam dataset, which is a large gallery of training images with known hotel IDs. I'll be discussing them a little later. And the goal of the competition is identify the hotels seen in the test images from the Traffic Cam dataset. There's no overlap between the test image and the training image, so they are completely separate. And it is like a basically reverse image search, or basically like an image similarity problem. The evaluation was mean average precision at IU5, which we'll be discussing again a little later. Few sample images. I'm not labeled them with their IDs. I can basically give a visual explanation of how it looked like. So in the directory structure, you have directories, for example, 1, 2, 3, which are basically the ID of the hotel chain. And inside each directory, you have multiple images for each hotel chain, which have IDs related to those images. For example, you can have in directory 1, 100 JPG, 101 JPG, 102 JPG. So all those images belong to category hotel chain 1 ID. And the right side are the test images. The data that they provided were image that is with the image ID, the chain, like I mentioned, the main root directory, which had the hotel chain. hotel ID for the image. Yeah. Hotel ID with target class. I'll be coming again later. I'm a little confused right now, the difference between image and hotel ID, because the image ID is a hotel ID. Timestamp, they also mentioned the timestamp when the image was taken. And then they had a sample of CSV. You had to basically submit in the correct format, which image matches with which hotel ID. The training images were approximately 97,000 images. If this sounds huge, we'll be talking about another data set, which is a very similar data set. It was almost 1 million images. So this data set was basically released so that researchers have more feasible data to work on as compared to 1 million images of data, which might not always be realistically in terms of storage. Now we'll discuss about the evaluation matrix, which this team used. I'm just going to do 1 second. Okay. Evaluation matrix, which this team used, they use mean average precision. So before we dive into MAP, I'll give a brief description about what goes before we reach MAP. So let's talk about, so one of the very common metrics is precision in any classification problem. So precision measures how accurate your prediction is. That is the percentage of your predictions, how many of them are correct. The higher the precision, the more confident the model is, and that it is classifying a sample as positive. But is it really a reliable matrix? Consider this image. I'm not sure if my arrow is clear. It's okay. Sorry. So consider the image shown in the slide. The red is the prediction and green is the ground truth. If you see the image, that it did classify the one object correctly, which was actually positive. So the true positive is 1. False positives is 0 because it did not incorrectly classify anything. So using the formula of precision, we have 100% precision. If we rely on this matrix, we will end up using this model and it will be a disaster. And as we can see, why? Because it is not really identifying all the other objects present in the samples. So what are the other metrics, reliable metrics? In classification model, we use something at the intersection, something which uses both precision and recall. So what is recall? Recall is how good your model finds of all the positives. For example, there were 10 positive labels, and the model found almost 9 of them correctly. Then it is almost a good recall. But there's a trade-off. Why? Now imagine the classification model. You have a 50% threshold, and you decided to lower a threshold to get more true positives. So as soon as you lower the threshold in any classification model, for example here, you will most likely get more objects being correctly recognized. But at the same time, the model will also start detecting targets which are not actually the ground truth value. So you do increase the precision, but because you're also increasing the false positives, you will be affecting the recall. So if you have a higher precision, you tend to get a lower recall. And if you have a high recall, you tend to get a lower precision. The solution is, so right now when we're talking about thresholds, we had a static threshold. The solution is usually to vary this threshold depending on the categories you have. So average precision will give you the average precision at average precision at all such possible thresholds, which is also mathematically similar to the area under the precision recall graph. What is MAP? If you have one class, correct me if I'm wrong, and please feel free to interrupt here. But if we have one class, mean average precision is same as average precision. But when you have multiple classes, then you're calculating the average of average precisions or mean of average precision over all the classes. For example, in the image on the right, we have average precision for airplane, airplane, average precision for airport, boat, and car. And the mean average precision is 0.56 because we are taking an average of all of the 4 classes that we have. Do we have any questions here before we move to the next slide? Okay, so code requirements. The code requirements are pretty standard, as I've seen for many Kaggle competitions. The CPU node, they had a defined runtime for CPU and GPU notebooks. For here, they had both less than or equal to almost 9 hours. Pre-trained models were allowed. Submission files, it has to be in a format of submission.csv. One of the confusions which I saw while reading the discussion board was they did not explicitly mention any rule for using an external dataset. And also, some people asked about the external dataset, but there was no response. So some participants ended up using, some did not end up using. And we'll have the solutions that we're discussing, will be a mix of both of them. So this is what the leaderboard look like. The one I have labeled are the ones which we'll be discussing. That is rank 1, rank 8, and rank 14. These 3 were the only people, only participants of all of the participants who actually released the methods they used, and none of them released any methods. So we'll jump to the solution of the first place winner. We were discussing them in the detail, but a quick summary, the methods they used. This person was smart enough to use an external data set since they did not say anything, the competition winners, and ended up using 1 million additional images, which is what the part of total 50K data set. This person also corrected some incorrect image rotations, did some data augmentation. The model used was ArcFace, which initially was developed for deep face recognition models. Backbone was Swin Transformer, regular NetY, and ResNest, which is actually a variant of ResNet. Optimizer is an RMW. Again, I'll be telling about it a little later. Scheduler was cosine NA. And again, as I was mentioning, Hotel 50K dataset, you can see at the bottom, it consists of over 1 million images from 50,000 different hotels. And the paper which this Kaggle competition paper released about the dataset, reading the paper, I realized that this competition had images which were sort of a little segment of images of the 1 million images which were part of 50K dataset. So they were not like mutually exclusive. They took us 50,000 from the 1 million images and then included them here.
Did they explain how they used the extra data?
Who explained?
I don't understand how the extra data was used.
The actual data, you mean the one which is provided the Kaggle competition, or the additional which was from the?
Yeah, the external data set, the hotels 50K.
When I looked at the description of the extra data, it was same format as the data provided in the Kaggle competition. So they also had a hotel ID, they also had images. So all the participants had to do was, if obviously they had enough resources, they could just fetch the data from wherever it was hosted and use it as a part of the competition.
Okay. Well, did they have the labels on the extra data?
Yes. Because
it's a completely labeled data set, I guess, right? These million images?
Sorry again, Bruce?
Oh, sorry. Really the same thing as Matt just said. But so there's a million images, but they all have labels in this data set.
I think so. They released the labels. I mean, because they did an analysis on the 1 million image data set on themselves. I'm assuming they also had images, or they would not have done, they would not have been able to do any deep learning methods themselves.
So maybe the competition test set was in the labeled hotels 50K data set.
I don't think so.
That'd be bad.
They mentioned that the training images came from that data set, but I did not read exactly what the test images, where they came from.
Yeah, I'm sure they were careful not to do that.
Sir, can I just ask a question regarding what is being classified here? Because with relation to your training and test data, I wasn't very clear on what was.
Okay. Let's go back. So the goal was to identify the hotels seen in the test images from the traffic cam data. So in the traffic cam data, you had a lot of images. You had to basically identify which in the test image had similar data in the train, or basically would say which hotel did they belong to. So as per the motivation of the competition, if in case of hotel trafficking, if you had test image, or if you had any unseen image suddenly, you could identify which hotel chain did they come from to actually go back to the hotel from where the source image came from.
Sorry, so that it seems that hotel room is being used as a trafficking location.
Yes.
Okay, I get it now. Okay, so if it's the same location, that's what we want to look for. Okay.
Yes.
Thanks.
No problem. So we were here. The pre-processing step done by this participant was, first he or she identified that there were a lot of images which did not have proper rotation angles, so they improved the rotation. They did not provide this person did not provide samples which they found, but this is from the discussion which they mentioned. So what this person did was he or she trained a classification model on the Hotel 50K, that is an external data set, and used it for correcting the rotations. So they did not mention how or what classification model did they use, but if they're using a deep learning model, there's something called rotate next, so they can just rotate all the images to whichever angle they prefer, preferably straight. The architecture, they did image representation. The image representations were trained by ArcPhase, and the backbone, that is a feature extractor, was swing transformer, regular NetY, and ResNest. So ResNest is just a variant of ResNet, which instead has stacked split attention blocks. I have not used it before, so if anybody has used this before, please feel free to jump in and explain this a bit. I found I've put a couple of snapshots of what regular NetY and swing transformer look like. So first I'll talk about swing transformer, the one at the right bottom. So swing transformer is an improvement, or it was supposed to improve the work of the transformers. And one of the benefit in that case in swing transformer, which I realized after reading, is that it helps in information flow between different layers. So if the different layers have window sizes which can vary, so if they have an overlapping window size in different layers, the information flow is easier from one layer to the other. I do not know what regular NetY or how it works like. It was a little complicated paper for me to understand, but when I read the paper, it was more like a design choice than the architecture choice, where they say that they generate a different block width for each. They generate a different block width for each block, and they and they have a key restriction for the regular net type of model, is that there is linear parameterization of block widths. Again, this was a design choice, which they mentioned in the paper, not the architecture choice. If anybody knows, even I'll be grateful to understand this. Does anybody here know anything about it? I will share the papers in which these came from by the end of the discussion. So I'll move to the next slide. The architectures. And in the architecture, they also mentioned the optimizer and the scheduler. The optimizer was Adam W. So Adam W optimizer is an optimizer which decouples the weight decay and the optimizer step. So because when we use Adam optimizer, the weight decay is explicitly bound to the learning rate. And so it has to basically optimize a new optimal weight for each learning step. So Adam W decouples them so you can optimize them separately. Then there's a cosine annealing. So cosine annealing is a type of learning rate schedule where you first rapidly decrease the learning rate and then increases. So when you're basically increasing after it had reached a minimum, you're somewhat like simulating it as starting a new ground for reusing the reused weights, which is how cosine annealing was used. This person used a bunch of data augmentation, and I mentioned all of them. They're just different ways of adding new types of data. Resizing, flipping, brightness, contrast, rotation, cutout, everything. It seemed like the person had an extensive data augmentation.
Sorry, one question. Going back to the scheduler.
Yes. Oh, sorry.
What was the scheduler doing? You mentioned it was used to change the learning rate. Is that what the scheduler is doing?
It was not changing the learning rate, but it is the way the learning rate was happening. So it started with a large learning rate and decreased very rapidly. And after it reached a minimum, and then it started increasing. So it did not follow the regular pattern of any other scheduler that is just falling down. And when it was at the minimum, they call this, at least the paper mentioned this, something called resetting of the learning rate, and it acted like a simulated restart of the learning process. And so it was able to reuse any good weights that they had accumulated, the model had accumulated by that time as a starting point. And so they could restart with a better learning rate when they had reached a minimum bottom.
Okay, thanks.
Again, if I'm not very clear, I really apologize, but I'll share the papers and the links again later. I was also able to read them while I was working for this competition. Next is the architecture. Now, I have never used architecture before, but winner first and winner 8, so we'll be discussing both of them preferred arc-based architecture. This image, which I have put, is from the paper itself. And the arc phase, when the paper was released, it was initially made for face recognition, deep learning for face recognition, and it had nothing to do with the kind of images we are dealing with. My intuition is that these people use arc phase because though it was originally for face recognition, it had a very high discriminative capability that it was able to distinguish between one image and the other very, very nicely. And hence it was possibly useful for distinguishing two images which are very different and bringing together two images which are very similar. This was my intuition of how arc-phase architecture was used here. Has anyone used or heard about this architecture before? I also came across this only this Kaggle competition. If no one,
I think that's a no.
Yes. So I've put the snapshot which they meant. I put the architecture which they mentioned. The center part of this image is what they basically use as a core part of their architecture. And I've highlighted the portion where they say, give a brief description. And they mention that for each logit in the structure, they calculate an arc cosine and get the angle between the feature and the ground truth weight. and they do something called angular margin penalty, and hence the main title of the paper is not arc phase, it is something called angular margin penalty architecture. And they use this, abbreviate the name to call arc phase. So this was the architecture they used.
I think this is really cool, and it does make some intuitive sense to me that a model that's very good at telling faces apart, because a face is actually quite similar in terms of features to another face. So, but a model designed to tell those kind of images apart would also be useful if you're trying to tell apart images that are pretty similar to each other. So that's cool. That's one thing I'm definitely going to take from this.
Yeah, that was also my intuition. Again, this author did not explain very clearly why he uses architecture, but from the paper, this was what I was able to figure out.
Sorry, just to clarify, so it's not with relation to the image, but the weights themselves?
Feature and the weights, yes, as per they say.
Okay.
Yeah.
Right. One other question. So in this picture you have the left-hand side, you're doing some convolutions or whatever, and then in the middle, there's this arc phase stuff, and then you go into a softmax. So is that the basic idea here?
I think the whole part, the whole image is what they're given one single whole process from beginning till the end. But the core idea of how they use similarity matrix is in the center. But yes, in their work, yes, this whole image depicts the whole process of getting face recognition. Was I able to answer the question?
Yeah, okay, thanks.
Yeah, I don't, this is a bit new to me as well, but it seems like, I think the general idea is you go from left to right, you create this embedding and you want to compare two embeddings, and it's pretty typical to take effectively the dot product of those two vectors, maybe normalized, and that would give you the cosine of the angle between them. What seems to be novel here and gives it the name is that they take the arc cosine. So they actually care about the angle, not the cos of the angle between them, and somehow that gives them better discriminative capability. That's what I'm getting out of this. I don't really know why it works.
Yeah, even I don't have a very detailed answer of why this worked, but the results show that, okay, this worked. Given a large amount of data, it worked pretty good, and we'll come to the results in the end. The next thing this person used was label constrained database augmentation. This was another part which the participant did not explain very well, and I have never used before, and it was very hard to find even on the internet. Thanks to Bruce, I was able to find a paper. I can share it on the chat. So on page 5 of this paper, you'll see a word called database side augmentation. And what the paper basically said was it replaces every feature point in the database with a weighted sum of the point's own value and those of its top k nearest neighbors, the KNNs. The bottom image in the slide is what the participant provided. And their idea was that if we use a database label constrained augmentation, they can increase the leaderboard score because database augmentation is affected by different classes of image representation. So if you have in case of fewer images, you can somehow probably augment and get more images. I was again not able to understand how they did it. They did not explain. The only thing they provided was this image and 2 or 3 lines about that they did this. And yes, LB means leaderboard, if anybody's not familiar.
Yeah, this technique was new to me as well. And yes, Srishti and I went back and forth on it a little bit. It seems kind of interesting. And apparently it's fairly common in the world of image retrieval. And the idea is, well, when they talk about nearest neighbors, from the examples I've seen, I don't know quite how it applies in this competition, but for the examples I've seen, the distance between these images is actually related to the physical distance in space as to of the thing being imaged. So you have, like the example I saw is a big cathedral, and you've got a picture of the upper part with the spire, and then there's this other part of the building, and then another part maybe on the other side, and they're all neighbors. And the idea is that they're really pictures of the same thing, but they're maybe not capturing all the features that would identify that thing. So by kind of using this weighted average of your nearest neighbors, for any given image, you're picking up some of the labels that are in the neighbors as well as in your own, and that's probably going to help you identify the image correctly because you're getting more features out of it. And for standard image retrieval, I think like K is usually 2, and I think in this case
5.
they use K equals 5. Yeah. The term of the role of this term, the distance, which I assume is what D is in this case. I don't know how we get the distance in the case of these hotel IDs, but anyway. Somehow there's a distance that I guess makes some sort of sense, and they pick up the features from that. But they add this extra term, which is in red with the LXI equals LXJ. So they want these nearest neighbors to be constrained to be of the same class, of the same hotel ID. They don't mix the features otherwise. I don't know. That's about as much as I got out of it. Seems like an interesting technique.
Sorry, a quick question regarding the embeddings. So generally when we talk about image embeddings, we're talking about unique features in the image. But in this case, like because there are hotel rooms, doesn't like one pillow in one hotel room have a similar structure and feature in another hotel room? So what are we talking about here when we talk about image embeddings?
I'm not sure if I have the correct answer, but it is also possible that the person has considered the chain ID while doing this, because if you remember, we have images categorized in a chain ID. So like one chain will have multiple images, another chain will have multiple images. So maybe they are trying to find the feature embedding in one particular chain, because maybe I would think that in a particular chain of hotels, there will be a little similarity and will be in contrast to an absolutely different chain. For example, Fairmont will be very different from, I don't know, in Western Inn, or maybe. Just something that came in my mind.
So they're looking for some uniform set of characteristics, maybe some kind of branding of some sort, maybe colors or something that makes sense in terms of correlating to a particular hotel chain.
Yeah.
Okay.
This is what it seemed like this person was trying to do. I wish they explained it a little more, and that is why I would encourage, if you go tomorrow, ask this question to this guy. I'll probably be there to ask this question to him if this person comes.
Okay.
Next is, yes, I think I already mentioned in the beginning, they've expanded their database. So I think I also mentioned in the beginning that the hotel ID, which they're using right now, the images that they're using right now, they're a subset of a huge database, the Hotel 50K. So I would assume that for a given hotel chain, if you have 2 images, or even 3 images in the hotel ID, the current data set, there may be 2 another in the Hotel 50K. So they can add both the images as a part of the same chain or same hotels. So this is another part of what they call database. expansion. And this is very related to what they're doing in label constraint augmentation. So they make an index in the bigger data set and query it in the smaller data set. And they combine them together and say, okay, now we have a larger data to work on. This is just to have more and more images so we can have better classification accuracy, which they eventually show in the end. They did an ablation study. So in what is ablation study? So basically, we want to see the contributions of the proposed components, that is these backbones, by comparing the model, and we'll remove one component one by one to see what influences more, what influences less. In the image on the right side, if you'll see the person has mentioned H50KA, the Hotel 50K is a data set, part A and part B. They gave an explanation. And for this, I need to give a little context. The Hotel 50K data set has two types of images. One is the images that have been pulled or scraped directly from the websites, some travel websites. And second is the images that people have themselves added to the traffic cam. So it consists of both of them. In our current data set, if it was part of the Kaggle, there was only the traffic cam. But in the original, they had both of them. So the participant said that, okay, Hotel 50KA is only traffic cam of the larger data set. And Hotel 50KB includes both the scraped ones and also from the traffic cams. So they did a mix, and they basically did a mix and match of different training sets and different indexes to see which backbone, which architecture worked better with which sort of data set. And let me see which was the best. So as per the public leaderboard, the spin transfer, the ResNet, they're very close. The last one and the second one seems to do pretty comparable to each other, the Swin Transformer and the ResNest.
One question I would ask the organizers if I was going to go tomorrow, but I won't, is why didn't they include this Hotel 50K data set as part of the training set, just as for everybody in the competition? It seems like it's completely appropriate and very relevant.
They did not mention it, that you could use it as an extra, which left participants a little confused because you're not explicitly mentioning it. So can we use it? Can we not use it? And this guy just played smart. He's like, I'll use it. You didn't say anything.
Yeah.
Something that Bruce mentioned earlier, one thing I'm suspicious of is whether the test set was in that same set too. Like
That's a good question. I hope it was not. That would be big cheating. Somebody was able to do it. I hope the organizer was very smart enough to not do that. It's possible that in the original 50K data set, they had a separate test data, which with no labels, and they could include a subset of that test data as a test of Kaggle competition. Again, that will also have no labels. I would assume they are smart enough to have different training and tests, even in the original, included in the subset space.
Mm-hmm.
And this, again, we were discussing about the database augmentation. Whatever this person did with database augmentation and this bunch of models, they found that database augmentation effectively improved the accuracy. And I think this was a reported score, which they reported in the competition, almost 85% of accuracy. The public and private leaderboards were pretty same classification scores.
Very impressive thinking about the task and thinking about those images, trying to map a picture of a room to a specific hotel of 13,000 hotels.
When I first saw this competition, I was a little confused in the beginning because if a room is lightly lit and it has a bed and a pillow, many rooms would look same to me. And I was strangely surprised to see that okay, you can actually figure out which room belonged to probably which hotel, or even if not a hotel, at least a hotel chain would also help to know. So
in terms of the classification, or is the data the specific hotel, like the chain and location, or just the chain?
So there were multiple chains given. It's not just one chain, multiple chains, and in each chain, they do not specify which hotel. They just give a bunch of images.
So it's the you're classifying the chain.
But I opened this. Let me see. Oh, okay, I'll have to see that again. But let me.
I'll look it up.
Yeah, let me see. What did they give? If they would have given hotel IDs, then it would be hotels in hotel IDs. Yeah, they gave hotel IDs. So it would be chain, hotel IDs, and images in each hotel ID. That would be the data that they provided.
So the hotel ID is like the specific hotel,
Yes.
At the corner of this street at this location.
Yeah, I mean, they did not give the address, but I would assume a very specific hotel.
Okay.
Yeah.
And that's the target, right?
Yeah, that's the target.
Yeah, given that they have a separate field for the chain ID and the hotel ID, I guess. Yeah, the hotel ID is not just the whole chain, but a specific hotel within the chain.
Yeah, that was a good question. So they have hotel chains, hotel IDs, and so like the target is the hotels. So you can find out from the image which hotel does it belong to.
Sorry, I'm just reading the competition, so like the submission file. It says for each image in the test set, you must predict a space-delimited list of hotel IDs that could match the image. So if there's more than one hotel ID that could match an image.
Are they soft predictions? Like maybe you give a probability to your top 3 predictions or something, and then if your top one isn't right, but the second one is, you still get some benefit from that.
You need that for
Okay.
I think in the evaluation, they mentioned that in your prediction, if the first is correct, they would stop at that and they would not see the others. So they will see the first correct label that you provide and they will stop at that. And they mentioned in the form of, if you've seen the evaluation, they would mention AAAB, something they've given the form of A, B's, and zeros and ones. And they explicitly mentioned that. I think that's a good question you asked, because I was a little confused why they mentioned that. And now because you asked the question, I know why they mentioned that.
Okay.
Now we'll go to the next solution, which is 8th place. I think second two people, the 2 other people did not use very complicated steps. It was a little easier to see what they did. A general overview of the method. They did not use any external data set, and they said that since there was no detail mentioned, so they did not end up using. They also used data augmentation and some rescaling of images and padded where it was needed. They used cosine similarity. They used optimizer, which is look ahead plus Adam W. I'll explain this a little later. They had a bigger embedding layer. So the embedding layer had at least half the size of the final targets. The image size, this person said that, okay, for him or her, 512 images size was giving better results than 256. And the model used was ECA NFNet, which is actually a pretrained model of ImageNet, and it's a variant of normal. So NF is normalization free net. And this author mentioned that they had come across this model in a Shopify Kaggle competition previously. They said for the hidden gem, and they ended up using it and got good results. So the models that they preferred are margin, cause face. Both of them were initially for face recognition. And they also made a very simple classification model, the backbone of EfficientNet. So they used 3 of them, and EfficientNet was basically one of the important backbones. The optimizer they used was look ahead, and Adam W. Scheduler was one cycle learning rate, and loss was cross entropy or a cost phase. Now, I had not used one cycle learning rate before. And after searching, I realized that in the one cycle learning was pretty simple. What they did is that you reapply the learning rate at every cycle, and here every cycle means every epoch. So just have a new learning rate at every epoch. So just a one term for one cycle learning rate. I think I had to. Okay, I think I mentioned, maybe I have deleted it, but I'll explain a little bit of, I've already explained what Adam W does. I'll explain the look ahead. So look ahead optimizer, what it does is, it was a recent, not a very recent, but relatively recent work, which came from University of Toronto. And as the name suggests, what they do is that instead of using one optimizer, they use two optimizers. And one optimizer, what it does is it looks at the weights which the second optimizer is predicting and sees what the best one is, and then uses it in their model. So from the title, one optimizer looks ahead and sees what the other optimizer is doing, takes the best one off it, and then use it in their model. This is what at least the paper said. I think I already mentioned initially that they use cosine similarity of the test images to the training data set. And in the ensemble, they calculated the product of similarities from different models and used the top 5 similar images. As for just like the first participant, for this participant, also the ensemble of models who worked the best. They gave them a 72% accuracy, almost 72.7% accuracy on a public leaderboard. This was almost a 10% of difference from the first participant. First participant had an 85% of accuracy. So yes, we'll be moving to the next solution now. So if anybody has any questions, I can take them right now. If not, we'll go to the next solution. This is the 14th place, and only the third, and this is the only third person who actually explained the stuff that they did before submitting the results. So a quick overview of what they did. They used pre-trained models from Fast AI and used an ensemble of 5 models, which we will see in the results section. This person also did not use any external data, did data augmentation like every other person. Optimizer they used was QH Adam. I had never heard of this before the Kaggle competition. And the one description I found, I have put it on the slide. It says it is a simple alteration of momentum stochastic gradient descent, which averages a plain stochastic gradient descent step with a momentum step. If anybody here has used it before or heard it before, please feel free to chime in. I had not heard it before this competition. And the scheduler was one cycle, just like the previous person. Did anybody here QH quasi hyperbolic Adam optimizer before? I think one thing I also saw in this competition was a bunch of people use a different type of things. I wish there was a little reasoning why one thing worked better than the other. It would have helped a little. The discussion was also very bland in the discussion section of the competition. People were asking, a lot of people were not responding. So I think the conversation was very slow for this competition. Next is the data preparation. They downscaled the images to the maximum size of 512, which they said was much better than going even downscaling till 256. So they stuck at 512 size of the images. And the augmentation that they used for the default augmentations of FastAI, since they were using the FastAI methods in the first place, which was padding and some transformations. Their solution using this optimizer and scheduler I've mentioned on the slide. So the first column, a bunch of names they have given: V3, V5, V7. The architectures were ResNet, DenseNet, and DenseNet was also 100. ResNet 50, ResNet 101, and DenseNet 161. And they used focal loss with only DenseNet 161. Maybe it was working for them for some reasons, but the majority, they use cross entropy loss. And so it looks like the last one worked best for them till 55.9% accuracy. This person also did an inference. The TTA, which is the test time augmentation. What is test time augmentation? It is basically when we are performing random modifications with test images. For example, when you're testing one image, you just don't test on the image itself. You rotate it, maybe transform it to have a more confidence of your model on the test image. So this person also did test time augmentation, or TTA, and got a 60.4% accuracy on the public leaderboard for the. So these numbers you see 3, 5, 7, 8, 11, K2 come from the model number in the first column. And 7, 8, 11, K2 are, again, V7, V8, V11, and VK2. These are ensembles, so they put it together. My concluding thoughts: using external data was definitely very useful. The final precision was mean average precision, rather, was almost up by 15%, but at first, by the winner. ArcPhase seemed to have performed very well, probably given a discriminative ability. This was my intuition. And also, like people right here said that it made little sense. Data augmentation, everybody did. It helped, and it's usually very common for all classifiers. Ensemble modeling worked best for all of them. So it was probably good for all the models that they tried. I did wish that the author one was a little detailed in the description of methods they used, so that it would be easier to understand what they did and why they did. Having said that, if you're interested in asking more questions or listening to the competition discussion yourself, it is happening tomorrow between 12:30 to 2:30 p.m. EDT. So feel free to chime in and ask as many questions tomorrow as you want. Especially most of them which we couldn't figure out today.
It's actually really cool that they're hosting one of these. Is this something that Kaggle is helping them host, like this competition discussion, or is this the sponsor of the competition that's hosting it? Or
no, the workshop people themselves are seem like they're hosting it on Kaggle, and they mentioned it's a research competition. That is why there were no prizes in the beginning.
But it's part of the CVPR conference, is that right?
Yes, it's CVPR conference has multiple workshops, and one of the workshops was fine-grained visual categorization, which and it has many of them. For example, they have I think a couple of months ago, Kaggle, this data science meetup also had an iWildCam Kaggle discussion. So that is also yearly a part of fine-grained visual categorization. This is hotel ID. Then they have something called FA for fashion. There are 6 or 8 of them. So yeah, and I think if we go to the first slide, this is what the land page look like. So you can find all other workshops or other competitions that are part of this workshop. Yes, that's the end for me. I'll share the link of the competition in the chat. This is the competition. I mentioned a bunch of optimizers, schedulers, other thing. I put it in a document if anybody has to probably read it later on, because not everybody would probably open the slides in the end after it has been recorded. So yeah, that's the end.
Well, thanks so much, Srishti. When you see diagrams and papers, you know it's going to be a good time. Yeah, I want to thank you again for providing this presentation and also delivering it. At the end of our presentations, we normally unmute our mics and give a round of applause at the count of 6 this time, because I like the number 6. Let's do 6. So 6, 5, 4, 3, 2, 1.